Hello and welcome to ICDD's InSession webinars. Soon you will hear ICDD's Executive Director Tom Blanton and ICDD's Manager of Engineering and Design Justin Blanton present 2D pattern analysis using PDF4+. Please remember to visit icdd.com for information on future free webinars, educational events, product information, and to purchase ICDD's databases and software.
Hello, everyone. Glad you could join us today. Great to have you here. I'm Tom Blanton, and I'm going to start with just a very short introduction on a few concepts regarding 2D diffraction analysis. And then I'll be turning the presentation over to Justin, who will talk about the 2D pattern analysis using the PDF4+. I'll be using some demonstrations in my presentation. The equipment demonstration that I have here is not an endorsement of the equipment or equipment manufacturer. It is used for demonstration purposes. And regarding the different manufacturers, I like all of them. So it's a matter for our teaching purposes today. For those who are interested in getting into the details of two-dimensional X-ray diffraction, I would strongly have you consider getting the 2D XRD book by Bob He, published by Wiley, and we will be providing this information in the question answer information that all attendees will be sent after the presentation is done. So just a couple things to consider when we talk about two-dimensional diffraction. The first X-ray diffraction pattern was in 1912. Von Laue, along with his graduate students Friedrich and Knipping, set up an experiment with a copper sulfate crystal. You'll see here on the right, this is the first X-ray diffraction pattern. The quality doesn't look so good because in the initial experiment, they actually had the photographic plate perpendicular to the crystal rather in the transmission or back reflection position, but they soon figured out how to improve the experiment. But this was really the first demonstration of X-ray diffraction and using a 2D detector, photographic plate, to get your image. From the powder world, in 1916 and working on it simultaneously, published in 1917, we had Debye and Scherer in Europe, Hall in the United States. And what they showed, again using photographic plates, was that you could analyze powder samples using the X-ray diffraction technique. There was a belief for a number of years that when you would grind up a crystal, that actually would result in destroying the actual crystallinity, crystal structure. That certainly is not the case. And in their initial images, they show that if you had a random powder sample, you would get these diffraction rings, referred to today still as the Debye rings. So to give you just some analogy on grounding us where we are when we're talking about different diffraction techniques, I like to consider single crystal versus powder diffraction. Single crystal is getting into the detail of looking at a single leaf, where powder diffraction would be looking at a distribution, a random distribution of multiple leaves. So when you do the single crystal experiment, if you irradiate that single crystal, you'll get a series of diffraction spots, Laue spots, and each spot represents a different lattice plane. When you look at the powder sample, you actually have a large number of crystals, and when they are randomly oriented, you get a summation of the spots so that you end up with diffraction rings. And that's really the comparison of the single crystal and the powder technique. You do have the situation where you can have what I would refer to as oriented XRD. And in this case, you have what would be a polycrystalline sample, but the crystallites are well aligned with each other. And so you end up with not the single crystal pattern, not the powder pattern, but something in between where you get some type of series of arcs that give you the indication you have preferred orientation. So this is where we come from when we're looking at the 2D detector type analysis. Now, in a conventional powder diffractometer, you would have some type of an X-ray source. You have your sample, and in this particular instrument, this was what we would refer to as a point detector, meaning it was collecting one data point at a time. So as you were scanning the detector at an angle 2 theta relative to the direct beam, you would then get your plot of intensity versus 2 theta. And when you look at that plot, the angle can be converted to d-spacing, which tells you something about the unit cell parameters. The intensities tell you something about the atomic positions, X, Y, and Z. And then your background tells you something about the crystalline and amorphous content. And this is your conventional powder technique using a point detector. Today, though, you have these silicon strip detectors, which are excellent detectors to use on your powder diffractometer. And you'll hear the term 0D, 1D, and 2D mode operation. Different manufacturers make these types of detectors, the hybrid pixel array. And the general idea is that you can be looking at a wider swath of your 2 theta as you scan the data. I'll show you a little demonstration in a couple of minutes. It allows you to collect data perhaps faster or higher quality. You can get more counts. These are really excellent, excellent detectors. When we use the term, though, 2D with this type of detector, what do we mean? Just as one example, if that detector is rotated 90 degrees, you now have a smaller 2 theta region that you're looking at, but you're looking at more of the gamma region here, so you will collect a wider range of your Debye rings, a pseudo Debye-Scherrer type data collection. Now, when we talk about large area 2D detectors, there are different examples. We have image plate detectors, which is a coating of a barium bromofluoroiodide, europium doped on some type of polymer support. This type of detector can be curved to fit a certain geometry. You have some of the flat detectors, such as multi-wire or silicon panels, where think of these as a very large silicon strip detector, but instead of using a strip, you're using panels that are stitched together, and you can get a wide area diffraction pattern. Some of the kinds of data you can collect, just showing some examples here. Powder data, where the detector is not set at the 0 position, where it is set at the 0 position, so you get the symmetrical pattern. An oriented pattern, like I talked about the oriented leaves, you get orientation of materials, different variety of patterns. Here's a pattern from a image plate where you can get a wide range of the 2 theta spectrum. And here's a case where you stitch together 4 frames of diffraction data to get more complete pattern based on the limitations of the area of the detector. So I talked about the strip detector, and how does that compare to your big large area detector? If you have a point detector, kind of consider that like a strip detector that has slits on it, so you're only looking at a small region of the detector, and you scan across the Debye rings of a diffraction pattern, you'll see just a small swath of the data compared to what you would see in a large area detector. When you have it in 1D mode, so that you're looking at a wide range of 2 thetas simultaneously, you can collect that same data, but much faster. And so you improve your efficiency in terms of your data collection. When you've rotated the detector and now you're in the pseudo 2D mode, you now will get a wider swath of the pattern, and it looks almost like the region you would get in a typical Debye-Scherrer type film experiment. So these are the different operations, but you'll see no matter which way you're using them, the area detector will still collect a wider range of 2 theta and Debye data. So a couple of examples here just to show what the 2D detector can do for you. Here's a microdiffractometer. You've got an X-ray source. You have a sample stage. You have a 2D area detector here. And first example is looking at polypropylene. Now, this is the case where you know what you're working with, but you want to see what's the effect of processing on your diffraction pattern. So if you take the polypropylene, you heat it up to the melt and you quench it very quickly, you get these very broad diffuse peaks indicative of a mesophase amorphous type polypropylene. When you heat that sample for 10 seconds at 120 degrees C, you'll see evidence of crystallization of the polypropylene. You'll always have a little bit of amorphous component, but you also have your polycrystalline peaks present. Take that sample now and stretch it in one direction 6 times its original length. And what you'll now see is that some semblance of the original pattern, but notice this peak right here seems to have disappeared, or at least most of it has disappeared. So it's telling you something has happened to the sample, but you don't get all of the information in the 1D pattern. So we turn to our 2D detector for the same samples, and you'll see that that cast amorphous sample still has broad rings, broad peaks you would see in your diffractometer, and it is indicative of a mesophase polypropylene. After you heat the sample, you'll see that in fact you're getting more narrow rings. It's indicative of the fact that you've induced crystallinity from heating, and you have random distribution of those crystalline regions. When you stretch the sample, you now got some preferred alignment of the crystallites, and that's why we see these arcs rather than rings. But it's not a true single crystal. You'll still see a little hint of some ring data, meaning that you don't have perfect alignment. But the key is that you'll notice that you have a series of these arcs in the equatorial position. These are HK0 diffraction peaks. And then you have this first line meridional. This would be an HK1 diffraction peak. And it's this diffraction data right here that is missing in the stretched sample. And the reason it is missing is that your point detector, your strip detector is scanning along this region right here. It won't see the diffraction data, and that's the advantage of a 2D detector. So again, the case where you know what you're working with, but you want to see microstructure changes. Here's an example where you're trying to understand what is the phase. This is called a K2 stone, and it's the green version. It's more commonly found blue, where the blue are little dots of azurite, but this has green dots on it, and it's a granite matrix, and the literature has indicated the green must be due to the malachite form of copper carbonate hydroxide. So we proceeded with collecting some data. This was data collected recently by Sławek Jasinski at Alfred University. And we have a little image of the area being irradiated, the laser beam showing the alignment of the sample, the X-ray beam doing the irradiation around the green spot. And you'll see that we have diffraction data, but it's not complete rings. You see the semblance of rings, but you see really some intense spots. And that's an indication that the area being irradiated is comprised of a very large crystals, or crystallites, I should say, and that there's enough of these to give some like I say, order of a ring, but because they're rather large, you only see a few, and so you're seeing individual diffraction spots. Now, this is a collection of 6 frames of data, and when you integrate all of the data here, you can then get a I versus 2 theta diffraction pattern, and you'll see that there's some complexity to the pattern that is here. When you go to do your phase identification, you'll see 3 principal phases: quartz SiO2, cristobalite SiO2, and atacamite, which is a copper chloride hydroxide. And what that tells us then is what we have recently discovered is the green phase is in fact atacamite, not malachite. So this is the first evidence that we've seen of someone collecting diffraction data, but using it on a microdiffraction system with a 2D detector was necessary to be able to get this data. The other thing that's important here and what's critical is the ability to use the powder diffraction file database so that you have accurate data, you have complete data, and this is what allowed us to actually get the correct and accurate phase identification. So I hope what I was able to show you is just a few concepts about the detectors themselves, about a couple things you can do with 2D XRD. And I'm going to turn it over to Justin, who's going to be talking about using the PDF4 to do 2D pattern analysis. So with that, Justin, I'll stop sharing and turn it over to you.
Okay, thanks, Tom. So I'm going to continue with this presentation, and I'm going to be focusing on a lot of the concepts that Tom had discussed, but we're going to be looking at how you can utilize these concepts using the PDF4 Plus software itself. So all the features I'm going to show you are available in all of the PDF4 databases, and in particular I'm going to be using the PDF4 Plus 2022 version for this demonstration. Okay, so in this webinar you're going to learn how to display 3 different types of simulations in the PDF4 Plus. So I'm going to first show you the ring patterns, SAED patterns, and EBSD patterns. So ring patterns are basically what Tom was discussing. Those focus more on the powder diffraction end of things, where SAED and EBSD patterns are actually more single crystal electron diffraction oriented. Then I'm going to show you how you can actually import 2D data into the PDF database software itself, and then how you can perform phase identification using that 2D data. Okay, so let's focus on the first type of 2D style pattern that you can simulate and analyze in the PDF database. And these are what we like to call ring patterns. So a ring pattern is a 2-dimensional or 2D simulation of the diffraction pattern for a given phase as it would appear on a flat 2D detector. And this can be such as photographic film, phosphor image plates, and solid state arrays. The simulation assumes uniaxial positioning of the detector, transmission geometry with incident beam centered, and an infinite number of randomly oriented crystallites. Now, ring pattern simulations are available for every entry in the PDF4 Plus database. So that comprises all 460,954 entries, which ring patterns can be simulated for. So the first thing you're going to notice on the right-hand side, where we have the ring pattern simulation, the left side of the window is the actual simulation itself. So the simulation is dynamically drawn on the left side. Now on the right side of the window, you have the user-definable settings. So you can dynamically change any of the settings on the right to change the simulation shown on the left. And you can see that the simulation, or the ring pattern simulation, comprises of a series of cylindrical rings here. And as you move from the inner ring towards the outer rings, you're moving from low 2 theta to high 2 theta. The more narrow the ring, that means the more narrow the peak profile, if you're used to looking at a typical 1D pattern, and the more broad the ring, the more broad the peak profile. Also, as with traditional 1D diffraction patterns, a more intense ring is actually going to be appear as a more brighter ring. And then rings that are lower intensity are going to seem to be less bright and more dim. So the settings for these simulations can be changed globally. So you can change these settings for all the ring patterns that you're simulating, or they can be changed on a per pattern basis. The different types of simulations that you can actually change are different types of radiation. So you can switch between X-ray diffraction, neutron diffraction, and electron diffraction, radiation types. You can also dynamically change the crystallite size of the ring pattern simulation, and I'll show you an example of this. And you can also perform an orientation distribution function, showing some simulated orientation for the ring pattern. And also you can import 2D images directly into the window for visual overlay. And I'm going to show a demonstration of this. Okay, so now we're going to move on to a live database demonstration. So I'm going to share the screen for my PDF4 Plus. Okay, so let's say we're working with silicon and I want to do some type of 2D analysis. So the first thing I'm going to do is a quick data mining search. So I'm going to click silicon in the periodic table. I'm going to switch all the other elements to no. And I'm going to focus on the silicon patterns in the LPF database, subset of the ICD database. And then I'm going to click the search button. So here are a list of all those silicon patterns. Now I have a particular entry in mind that I'm going to focus on, and this particular silicon pattern is here. So to open up the PDF entry that you want to look at and analyze, you simply double click that entry in the table. Okay, so here's the PDF entry for silicon that I'm going to work with. Now to open or create a ring pattern simulation, look at the top toolbar and you'll see a button that says ring pattern. So simply click that button and that's going to bring up a simulation of the ring pattern for that entry. And this entry is the silicon pattern that we're looking at. So I'm just going to expand this window so you can see it better. Okay, so as I'd mentioned, if you look on the right-hand side, you'll see a list of different settings. So right now it's set to X-ray diffraction, and we're looking at the copper wavelength, but you could change to neutron diffraction or electron diffraction. So we can simulate different types of diffraction types. You can also change different wavelengths. So if you wanted to, let's say, change to Moly, you could select Moly here. Or cobalt. So whatever type of radiation you work with, we can handle that. So I'm going to go back and select copper here. Now there's also other settings such as the plot size. So if you want to zoom into the ring pattern like I'm doing here, we can actually decrease the plot size. You can also dynamically change the crystallite size of the simulation. So this slider under crystallite size, if I drag this to the left, we're going to decrease the crystallite size, which is essentially making the rings more broad. So if I make it really low here, you can see how the rings start to get really broad out here. And then if I increase the crystallite size, the rings or the peak profiles start to get more narrow. So now I'm increasing it very high, and now I'm at 1,000 angstroms. So we have very narrow rings here. So now what I'm going to do is I'm going to show a demonstration how you can import a 2D image for visual analysis. Okay, so to do that, you're going to click on the File menu on the top left, and then we're going to select Import Diffraction Pattern. Now, we support many different types of 2D patterns. So we support different vendor formats, and you can also import any type of image format, like a JPEG or a PNG or a TIFF. So I actually have a file type here. This actually came from a Pilatus, a Detectors Pilatus detector. And then I'm going to select this file here, which is a .cbf, and then I'm going to click Open. And the first thing you notice is that now we see the 2D image that we imported overlaid as the background of my simulation. So I'm going to go over here and check the transparency button. So now we see the pure 2D image. So this is the 2D image of silicon that we imported from our CBF file. Now I'm going to add the simulation back on top, and you can see now these red rings that are essentially being simulated on top of the rings in the image. those are the rings from the simulation for the PDF entry in the database. Now I'm going to show you that by zooming in so we can get a more clear picture of that. Okay, so now let me actually lower the transparency, and now you can get a better view of these red rings, which are the simulated rings. So these are actually the despacings for the PDF entry of silicon, and you can see how they actually match up pretty nicely to the rings in the 2D image that we'd imported. You can hover your mouse over the rings and actually get the 2 theta value, you can get the despacing value, you can get the intensity, and you can also get the HKL Miller index value. So now we can actually use this simulation, which is being simulated on top of the image, to actually find out what the despacings are of the 2D image that we had imported. So simply hover your mouse over the rings, and that'll tell you the information about that ring. So this is a really nice way where you can take an entry in the database, you can import a 2D image, and then you can essentially use that PDF entry to determine what the rings are that you're looking at in the image. You can also change the color of the ring. So I have it set to red, but you could also set to maybe blue if you wanted to use blue. We also have an intensity multiplier. So as I increase the intensity multiplier, what that is doing is it's taking some of the lower intensity rings, which are higher out in 2 theta here, and it's making them more visible. So you can see how those match. Okay, so that's an example of the ring pattern simulation. So I'm going to go back and then share the demonstration or the PowerPoint. Okay, so let's move on to a different type of simulation. So now we're going to look at selected area electron diffraction patterns, also known as SAED patterns. So this is actually a type of single crystal simulation in the database. So as Tom mentioned, this is actually different than a powder diffraction simulation. Now we're looking at single crystal here. So an SAED pattern is useful in confirming phase identity, crystallite orientation, and crystalline symmetry. The spots that you see on the right-hand side, so instead of looking at a series of rings, now we're looking at a series of varying spots of varying intensity. These spots are determined kinematically using unit cell parameters and space group extinction conditions associated with the PDF entry in interest. So sometimes these are actually colloquially called spot patterns. Instead of just calling them an SAED pattern, you can call them a spot pattern because like a ring pattern, which is a series of rings, this is a series of spots. So SAED patterns or spot pattern simulations are available for 410,156 entries in the PDF4 Plus 2022 database. So again, a good majority of the entries in the database can be simulated as spot patterns. So if we look at the window on the right, like the ring pattern, we show the simulation on the left-hand side of the window. So you can see the simulation of the spots here. And then on the right-hand side, we're showing the user-definable settings. So we try and keep the user interface consistent across all different types of simulations. So as with the ring patterns, with the SAED patterns, the settings can be changed globally or on a per pattern basis. There are different types of simulations that you can set. So you can set different camera settings. So if you know the camera constant or the camera length of the detector that you're using, you can set that. You can also set the energy settings. So you can enter the voltage or the wavelength of the instrument that you're working with. And you can also define the zone axis that you're going to be looking at for the spots. There's also an interactive despacings table on the bottom right-hand side, and I'm going to show you how that works in a demonstration. And like the ring patterns, you can import images for visual overlay. And new for the 2020 database, we've added an SAED extension module, which actually gives you some more advanced features in terms of simulating the spot patterns themselves. Okay, so let's go back to the database for a live demonstration. Okay, so I'm going to close out my previous windows. And now I'm going to work with gallium nitride. So if I want to look at all the gallium nitride patterns in the database, I can simply click on gallium here on the periodic table and nitrogen here. And then I'm going to click this button to exclude all the other elements. So we just have gallium and nitrogen selected. And then I'm going to click the search button. So here's a list of all the gallium nitride patterns in the PDF4 Plus database. So we've got a list of 32 of them. So I'm going to select this first entry here. This is a star pattern, so it's a high quality gallium nitride pattern. And I'm going to open up that PDF entry. Now to open up an SAED pattern, also known as a spot pattern, again, if you look at the toolbar on the top, you're going to see a button that says SAED pattern. So simply click that button to open up the spot pattern. So I'm going to maximize this so we can get a better view. Okay, so first thing you'll notice, we have a series of spots. And if you hover your mouse over any particular spot, it's going to show you the D-spacing and HKL for that spot. So this one here is 3.6208, and the units that we're working with are inverse nanometers because that's a typical unit that an electron diffractionist would be working with. However, these types of units are actually customizable, so if you're more familiar with working in terms of angstroms, I can go over to the right here, change the label to D-spacing in angstroms, and I can go back and hover my mouse over and it says this is actually 2.762 angstroms. So it's completely customizable. All right, so let's import an image for analysis, and then I'll show you how you can change some of the dynamic settings for the simulation. Okay, so before we import the image, I want to calibrate my settings to match my instrument, or the instrument that was used to generate the spot image that I'm going to import. So the first thing is I know what the camera constant value is for my instrument, and I know it's 1.1. So over here on the top right, I'm just going to type in 1.1 for the camera constant. And you can see that the simulation on the left automatically resimulated to the new camera constant. Now the next thing is I want to look at a particular zone axis that I'm working with. So under zone axis, the default value, which is 0, 0, 1, I'm going to change that to 0, 1, minus 2. So again, you can see now we've recalculated the simulation, and there's actually less spots being visible here. Now the last thing I want to do is I'm going to go down here, and where this checkbox says hide minimum intensities, I'm going to uncheck that. And once I do that, you're going to see that a whole series of spots have been added. So this allows us to see some of the low intensity spots that maybe normally we wouldn't really be that interested in. But since I'm importing a spot image for visual analysis, I want to include all the simulated spots if possible. Okay, so now that I've calibrated my settings to match my instrument, I'm going to now import the SAED image for visual analysis. So I'm going to click on the File menu on the top left and select Import Diffraction Pattern. Now we support various different types of image formats such as JPEG, GIF, PNG, and TIFF. So for this, I'm going to select which is a JPEG file here, and I'm going to click the Open button. And now you can see that we've overlaid the SAED image on the background of the simulation. However, we want to do some things to better differentiate the simulation from the image. So the first thing we want to do is actually change the color of the simulation to better differentiate it. So I'm going to go back to my settings on the right, and this drop down where it says foreground color, I'm just going to change that to red. So now we have the spots simulated in red, and it's a lot easier to now differentiate those between the spots in the SAED image that I imported that's drawn in the background here. Okay, so now the next thing I want to do is I actually want to rotate my simulation, because you can see that the SAED image has been rotated. So we're going to go over on the right hand side here, and under where it says rotation angle, I'm going to click these arrows and start rotating the angle downwards. So this is actually going to rotate the SAED pattern counterclockwise. And as I do this, you can see that the spots start to line up with the spots in the image. So once I get to about -56 degrees, you can now see that the spots in the simulation are now lined up, parallel to the spots in the image that we had imported. Now lastly, we want to recenter the simulation to fit the 2D image. So an easy way you can do that is actually just hold down the right mouse button, and you can just drag the simulation and move it with your mouse, as I'm doing here, until you see the spots line up with the image. Okay, so now we're getting a pretty good alignment here, and you can see as I move the simulation with the mouse, the center value over here on the right actually recalculates to the new position that I had dragged the simulation to. Okay, so now we have our simulated spot pattern, which are the spots in red. These are simulated from this gallium nitride pattern in the PDF database that is now being overlaid on top of the spot pattern image that we had imported, and those are the spots in white. Now from here, we can actually use the despacings table on the bottom right to tell us or identify what the spots are in the image. So let's take this big spot here. If I hover my mouse over it, it says it's 2.762 angstroms, or a 100 Miller index, or HKL. So if I click on this spot, it's now highlighted in orange, and that's actually a customizable color. But if we look at the bottom right-hand side on the despacings table, that particular despacing or spot is now checked off. So now we can kind of get a running list of what despacings that we want to identify. So let's say I want to click on that one, I want to click on this one here, and then I'll click on this one here. So I have these two larger ones. Now let me get this one here, and then this smaller one here. So now we've identified these three spots in the image that we imported, and if you look at the table, we can see those spots. You can see the despacing values, the HKL values, and also the relative intensity of those spots here. So this is a really nice way of importing an image and then using the simulation to identify the despacings and intensities and HKL values of those spots. Now alternatively, you could actually just check on a despacing in the table itself. So let's say you're looking at the despacings for 0.587 angstroms. So if I click on those in the table, you can see now those are automatically being highlighted in the simulation here. So there's a nice correspondence between the simulation and the image and the despacings table on the bottom right. So that's an example of how you can use the SAED pattern simulation, also known as a spot pattern simulation, in the PDF database. All right, so let's go back to the presentation. And now I'm going to show you a third type of 2D simulation in the database, and this is what we call the electron backscatter diffraction simulation, also EBSD shorthand. And like the SAED pattern simulation, this is a single crystal simulation, single crystal diffraction simulation using electron diffraction. So this is useful in confirming phase identity, crystallite orientation, and crystalline symmetry. Now, instead of looking at a series of spots like we did with the SAED pattern, or looking at a series of rings like we did with the ring pattern, we're actually going to look at a series of parallel lines, also called Kikuchi lines. So if you look on the right-hand side, these are essentially series of parallel lines, and it forms this nice kind of geometric image here. And those line positions are determined kinematically using unit cell parameters and space group extinction conditions associated with the PDF entry. And like the SAED pattern, EBSD pattern simulations are available for over 410,000 entries in the PDF4 Plus 2022 database. So for a good majority of the entries, you can simulate one of these EBSD patterns. So if we look at the window, we have the simulation on the left, and we also have the settings on the right. And the settings can be changed globally or per pattern. And because this is a single crystal diffraction simulation using electron diffraction, it's actually kind of using the same science in the back end as the SAED patterns uses. So you're going to have the same simulation settings. You're going to have camera settings where you can change the camera constant and camera length. You have energy settings where you can switch between voltage and wavelength. And you can also define the zone axis of the view of the simulation. Okay, so now let's switch gears and focus more on how can we actually import 2D patterns into the database for phase identification. Okay, so in this segment of the presentation, we're going to be focusing on the first type of 2D simulation that we had talked about, and that's the ring pattern simulations, because this is a powder diffraction pattern simulation. So in the PDF4 Plus database, if you have the Civ Plus plugin, that will allow you to import 2D diffraction patterns for phase identification. We support many major instrument file types such as Bruker, Detectors, ESRF, and Rugaku file types. So when you import a file type that was taken from a vendor format, those are nice, but because we can extract the detector and image settings directly from the metadata in the file. So as a user, you don't have to worry about what type of wavelength the pattern was taken at, or the tilt angle, or the camera to detector distance. And you definitely don't need to worry about the image settings, such as the XY scale and where the center of the diffraction pattern is located. All those crucial settings which are used for the identification of the material, all those settings are actually extracted from the file itself and are automatically populated into the program. Now we do support importing traditional image file types such as regular images such as JPEGs, GIFs, PNGs, and TIFFs. However, in this type of case, as a user, you will have to manually enter the detector and image settings to do your phase identification. So you will need to have that information. So if you look on the right-hand side here, you'll see here's a ring pattern, and this is a ring pattern image that we imported. And essentially what we're going to do is we're going to take the detector and image settings that were extracted from this file, and those are populated on the top right-hand side here. We're going to take those settings and then we're going to integrate around the entire pattern and generate a 1D diffraction pattern, and this is shown on the bottom right-hand side. And once we have this 1D diffraction pattern, we can use some of our traditional phase identification algorithms for the identification. We also support importing multiple 2D frames simultaneously. And sometimes with 2D diffraction patterns, you'll actually have more than one frame of the image taken simultaneously, and we can support that as well. So I'll show an example of that. So how does the phase ID process work with 2D diffraction? Well, you import a 2D diffraction pattern, as I'd shown. The program Civ Plus, which is a part of PDF4 Plus, will actually automatically integrate that 2D pattern down to a traditional 1D pattern. Once you have the 1D pattern, you can do techniques such as background removal, smoothing, and stripping of the K-alpha 2. And that allows you to extract the peak positions, which are essentially the fingerprints of the material. And once you have those peak positions, you can use search algorithms to identify the phases of the material using a reference database such as the Powder Diffraction PDF4 Plus. So that's kind of how the whole thing works. Now, in Civ Plus, we allow you to compare 2D diffraction pattern images directly in the program. So if you look at the Civ Plus window on the right, on the top hand side, we're listing the matches for that particular phase. So in this case, we're looking at aluminum oxide. And then on the bottom half, you will see the 2D analysis. So this is going to show the 2D image and the 2D simulation of the patterns that you're working with in the PDF4 Plus. So we allow a split view for easy comparison. You can enhance the contrast of imported images. And you can dynamically change the crystallite size of the 2D simulations, similar to what I showed in one of the examples in the beginning. You can also increase the brightness of low intensity rings. And now I'm going to shift to a live database demonstration and show you some examples of how this is done in action. So time permitting, I'm going to do 3 examples. The first is going to be from a Rigaku 2D detector, which was using cylindrical geometry. The second was a Xenox detector, which is using flat geometry. This is going to be a low angle pattern. And the third is actually from a Bruker detector, which we're actually going to import 4 frames of data simultaneously for the analysis. Okay, so let's switch over back to the database. And we're going to open up Civ Plus, because Civ Plus is the phase identification plugin in the PDF4 Plus database. So on the top toolbar, you'll see a button that says Civ Plus. So we just opened up Civ Plus here. Now we want to import a 2D pattern for analysis. So to do that, on the top left-hand side, you'll see a button that says Import 2D Diffraction Pattern. So we're going to click that. Now I'm going to import my Rigaku pattern here, which was taken from a rapid IP detector, and I'm going to click the Open button. And now you can see we have the 2D image on the top left-hand side. So this is actually the raw 2D image taken from the detector. And an interesting thing about this example is that because the detector is using cylindrical geometry, the rings are actually not perfectly circular. They're kind of more like an ellipse. But we can still handle this type of pattern for analysis. So we've extracted the instrument and image settings from the file, and we've populated right on the top right here. So you can see we're working with X-ray diffraction, 0.71 angstroms wavelength. We've put in the camera to detector distance. We've put in the image scale settings, and the center of the 2D pattern has all been calibrated. And using those settings, we can now integrate that down to a 1D pattern that you see on the bottom right-hand side. So now I'm going to take this and then click the Process button, and I'm going to select some predefined settings and do a peak search on this integrated 1D pattern. So if you're not really familiar with 2D diffraction analysis, but you are familiar with typical 1D diffraction pattern analysis, you'll probably recognize this type of pattern and how you would do a typical peak search here. So we've identified most of the major peaks here. I do recommend that you if you have time to fine-tune the peak search, you can always add peaks that maybe the algorithm missed, or you could also remove peaks that perhaps were due to noise or maybe some artifacts from the integration. But for the purposes of time, we're just going to kind of take this as is, and then we're going to import this pattern for phase ID. Now, the last thing before we do that is that we're going to select the mineral-related subfile here. Because I know I'm working with a mineral, it makes sense to only look at the mineral patterns in the database, and this allows us to avoid false positives. So I'll click the Apply Filter button, and now it's going to do the search in the database, and you can see at the top here, it's found aluminum oxide, or corundum, as the match. So on the bottom, you can see here's the 2D analysis, and I'm going to expand this window here and zoom in. So I'll zoom in to about 200%, and you can see the top half, these rings in white, that's actually the top cross section of the 2D image that we had imported. And the bottom half, the rings in blue, are actually rings simulated from the PDF entry that I have currently selected in this matches table. So I can hover my mouse over a ring, which will allow me to see the 2 theta, despacing, intensity, and HKL value. Let me zoom in a little more just so we can get a even clearer image. But you can see that we can actually match up the rings of the image and the rings of the simulation quite nicely here. It does look like the crystallite size of the simulation is perhaps a little high. So you can do a quick estimate of the crystallite size by just simply dragging the crystallite size slider down. And if we drag it down to about 360 degrees, what that's going to do is that's going to effectively resimulate the pattern. And I could even do it even lower. We'll do it down to about 250 degrees, or 250 angstroms, I'm sorry. And now we're starting to match the crystallite size a bit better. So here is the 2D analysis that we were able to generate. We were able to match it to corundum. Now we can always go back and look at a 1D view of this. So if we click on the 1D diffraction pattern view on the left here, now we're looking at this pattern in red. So the red plot is the integrated pattern. That's actually the pattern integrated from the raw 2D data. The blue pattern is the simulated pattern from the database. And even though the crystallite size actually looks pretty decent, we could always fine-tune this if we wanted to by dynamically changing the crystallite size here. So here is the 1D view. Okay, so let's try another example. Real quick, I'm going to import another 2D pattern. So this one was taken from a Xenox detector. And what's interesting about this example is that the contrast is fairly low. So I'm going to click on the Enhance Contrast button to bump that up. It doesn't change the integration or the analysis, but as a user, it helps me see where the rings and where the despacings are. Now, one thing you'll notice with this particular example is that if we look at the integration on the bottom right, we've got this big jump in intensity here. And that's due to this brightness, as you can see in the center of the image. So this brightness could be caused by various things such as air scatter, but what we want to do is we want to essentially integrate and exclude this area during the integration. So to do that, under integration here, we're going to click the Integrate Sector button. And now this allows us to drag with our mouse. So I'm using my mouse here, and I'm dragging out the area I want to be integrated. So I'm going to take this inner ring here and drag it out so it starts to exclude that brightness, because we don't want that brightness to negatively affect our integration and subsequently phase ID. So this inner ring, which is the low 2 theta value, has been excluding this area. Then I'm going to drag the outer ring, which is the high 2 theta value. I'm going to drag it right outside near the edge of the image so we can just get as much data as we can. And then I'm going to exclude these dead pixels here because we really don't need that as part of the integration. Okay, so now you can see on the bottom right hand side, we don't have that large extraneous jump in intensity. We've got now 4 clearly defined peaks. So now we'll click the process button, and I'm going to change my process settings, and now I've gotten those 4 peaks identified. So I'll click the import button here. And for this example, I'm not going to select any matches filters. I'm going to click Don't Apply Filter, and I'm going to search the entire database. Okay, so now you can see that we've actually matched silver behinate, which is a low angle diffraction pattern in the database. You can see it's now matching these 4 rings pretty nicely. However, the crystallite size is fairly low because that's left over from the previous example. So I'm going to increase the crystallite size so it better matches the rings. And let me zoom in here so you can get a really nice view. And you can see how these rings of the image, where the rings in white, match up really nicely to the rings in blue. Now let's zoom out a little bit here, and you can see that there are some low intensity rings, so we can always use the intensity multiplier to kind of bump up the intensity of those rings just to give us a better view of where they are. So here's the 2D analysis of the silver behinate pattern that we matched in the database. And as with all 2D analysis, we can always go back to the 1D view, and we can adjust the crystallite size here. And now we're matching the silver behinate pattern in the database with the integrated silver behinate 1D pattern from the image. And we've got a pretty nice match and a nice match in crystallite size. Okay, so for the last example, I'm going to show you how you can actually import multiple frames of data simultaneously. So I'm actually going to select 4 files at the same time. So you can do this by clicking on a file here and either holding down the control key as I'm doing, or you could hold down the shift key, and you want to make sure that all files are highlighted here that you want to import. So we're actually going to import all 4 of these files at the same time. And now that I have them highlighted, I'm going to click the open button. And now you can see what's happening is that the program is automatically going through and integrating each frame or each pattern one by one, and then plotting those patterns onto this 1D plot here. And each frame or each pattern is actually a different color. So this better differentiates which frames are integrated here onto the plot. So if we want to look at a better view of the 2D pattern, we can expand that. And if you click on the drop down button for the frame, you can switch between the different frames if you wanted to fine tune the integration. But the integration over the full patterns actually does a pretty nice job of integrating these 2D patterns down to 1D patterns here. Okay, so you can see we've got 4 individual plots. We got a red, a blue, a green, and a magenta plot all plotted down here. And then now I'm going to click the process button. And now what you can see is that the program has automatically merged and stitched all 4 integrated plots taken from the 4 different files that we imported and merged them into a single unified plot. And you can see we've now identified all the major peaks here. You do sometimes get some mild artifacts from the integration and sometimes the merging of the patterns, but those typically do not interfere with the phase identification. Okay, so now that we've done the peak search, I'll click import. And like the first example, I know I'm working with a mineral, so I'm going to click mineral related and click apply filter. And now it's come up with silicon as the match for this phase. And you can see now on the bottom where the 2D analysis is, we're actually showing 4 frames simultaneously. So there's actually 4 cross sections here. And as we look at the first one, you can see this goes from about 100 and I would say 7 degrees 2 theta down to about 72 degrees. And each one is actually showing a different set of 2 theta range. But what's really nice is that you can actually change the crystallite size for all 4 patterns simultaneously. So if I lower the crystallite size here, if I want to make it really broad, I can do that. And it does it for all of them simultaneously. Also, I can change the x-axis. So right now I'm looking in terms of 2 theta space, but I could change that to despacing space. So now we're looking at in terms of despacings. So we can go to the 1D view here, and I can change the crystallite size to better match that data. So if you want to analyze it in 1D view, you can certainly do that here. But really, the point of it would be looking at the 2D view as we're doing here. And we can also zoom in and get a much better view of these diffraction rings and how they match between the image, which is these rings on the top, and the simulated rings, which are the rings on the bottom. Okay, so now let me go back, since we're running out of time here. Again, as I showed with the previous example, you can import multiple frames, and I don't show this now for purposes of time constraints, but we do have a 7-frame example, which actually matches nicely to aluminum oxide. And here's an image of Civ using a 7-frame example where we actually have 7 frames of data being simulated simultaneously, and you can do that visual analysis here. So pretty nice stuff with doing the multi-frame analysis. Okay, so now we're going to move on to the Q&A section, and I'm going to stop sharing my screen.
Okay, excellent, Justin, and thank you for your presentation. We do have a couple of questions, and I'll start with one that I had partially answered. A question came up was that can you export an integrated ring pattern for use in JADE, or for that matter, other software? But the question is, once you've integrated a 2D pattern, you've created the 1D pattern, a little bit about how you would then save that, and you can then import that into, for example, the question is asking JADE software.
Yes, so you can do that, and let me share my screen. Okay, so let's see. To do that, so I'll just take the last 4-frame example that I was working with. So the easiest way to do that would be to right-click on the 1D plot, because we want to export the 1D, the integrated 1D pattern. So right-click that, open a new window, and then you're going to click the File button, and then you're going to select Save. So there's different file types. Let's say you wanted to save it as a CSV. You could do that here. Just type in sipowder.csv and click Save. And then you can take that file and import it into JADE. So you could do your phase identification in JADE, or any type of diffraction analysis software that would support that file type. So again, right-click, select Open a New Window. So that's going to essentially bring out the diffraction pattern into a separate window, and from there, click File and Save.
All right. Thank you, Justin. There was another question here about could you give an example of a thin film sample that has missing peaks in the 1D pattern but gives peaks in the 2D ring pattern? So I'm going to share my screen for just a moment. And this is a 2D diffraction pattern. This was provided by Mark Rodriguez at Cyndia National Laboratories. And this is a 2D pattern of PZT, a thin film on a silicon crystal substrate. And what you'll see here is that you get some of the data from the silicon itself. The thin film is highly oriented, so you would not see all of the data in your powder diffractometer. If you scanned across the equatorial region here, you will miss some of the data based on the fact that your 1D type detector simply doesn't cover enough area. So this is an example, and the sort of the interesting thing about this particular one is Mark would refer this to as the pumpkin 2D pattern, because when you rotate it 90 degrees, you have the smiling pumpkin face. But that is, in fact, an example of where the 2D detector would get more information for you than you would find in just a conventional diffractometer. Okay, let me just check here because we have run through our time. There are questions we don't get answered today. We will answer them for everybody. Let me just look at one here. Justin, it says, what is the layer function in the SAED simulation?
That's a good question. That's something that we'll have to get back to you on, so we can give you a better understanding of that.
Okay, and then the final thing is, I'll just look at a quick one. Who have a question for crystallite size? How is the instrumental broadening accounted for? And I'll add a comment around that the function we used was an algorithm designed by Paolo Scardi and Matteo Leone. And what it really looks at is a crystallite, and it's looking at distribution, and then you get the number plus the variance. It does not take into account the instrument broadening. So if you're using an instrument, it's going to be a nominal crystallite size, but you do not have, like in for example, a Scher technique where you subtract out the diffraction width of a lab 6 or a silicon that you've run for the sample. It's looking at the entire profile, and based on the profile, it is in fact assigning the crystallite size. An important point to make is that if you have broadening due to, for example, microstrain in the sample, defects, etc., it does not take that into account either. So what it is doing is giving you a relative effect on crystallite size that you can quickly assess samples that are being analyzed by yourself. All right, so what we'll do here is we'll now conclude for today. I want to thank Justin for his presentation. We hope that everyone who's attending found the presentation to be useful. We will get a list of the questions that were asked, the answers, and we'll provide those to everybody. And with that, I'm finished with Steph, who has one more comment to make.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on ICDD.com. Contact us at info@icdd.com.